Hello there, Algebra 2. We are in Chapter 2, Section 3 right now. We're going to start out with a little warm-up that reminds us what we did in Section 1, I think. So, simplify the expression. If you remember some of our rules on exponents, when you multiply two monomials with exponents, you add the exponents. So I've got negative 3 times 5 is 15, and x to the third and x to the first would give me x to the fourth. Here, I'm subtracting like terms. They're both x to the first, so I can just subtract the coefficient and keep the variable and exponent. Here I'm going to collect like terms. I've got an x or y squared, a negative y squared, a y, and a constant. So when I collect like terms, I can only add things or subtract things that have the same variable and exponent. So 10 minus 8 is 2y squared. I only have one y and one constant, so I get the full answer. Here I need to distribute first before I do anything. So I'm going to distribute this, and I get negative 20a plus 24. And then I need to distribute this. That would give me a minus 2a plus 16, because that negative transfers through also. It distributes through also. Then I collect like terms. Circling my a terms, circling my constants. This gives me negative 22a, because I got a negative 20 and a negative 2. And then 24 and 16 is 40. So here we have each side of a square is 2x plus 5. Write an expression for the perimeter of the square. Perimeter, I add all the way around it. Okay, it's the length of each side added together, or 2 times the length plus 2 times the width, or 4 times one side. Since it's a square, we can add 2x plus 5 4 times, or we can do 4 times 2x plus 5. That gives me 8x plus 20 inches. Okay, let's get into today's lesson. So in this section, we are going to learn to add, subtract, and multiply polynomials. We're going to start out with the easier stuff, which is adding polynomials. We're going to practice it a few different ways. First, we're going to practice vertically, which is up and down, which can be much easier. We're going to line up everything that has like terms. So first, I'll write the first one. And then I need to line up everything in the second one. So I'm adding, oh, I see a typo. It's funny I call it a typo. I'm adding everything below the same term, which has the same variable and same exponent. A positive 6x squared. I don't have any x terms, so I'm leaving that blank. And I'm adding everything. So now I'm going to add vertically. 2x cubed plus x cubed is 3x cubed. Negative 5 and positive 6 is a positive 1x squared. I don't have any x's, and negative 9 and positive 10 is 1. So I rewrite it all, and I get my answer pretty simply. Okay, when I say in a horizontal form, that means this way. It means I just scan the problem and circle any like terms. So this is my only cubed. I'm going to circle my squared. Notice I'm circling the sign that goes with them. First power, and constant. So I can collect things that are the same color. I have 3y cubed because there's no more. The blue one's a -2 and a -4 gives me a -6. I always cross them off when I'm done because once they're all crossed off, I know I don't need to add or subtract anything. I've gotten them all. I haven't left anyone behind. A -7 and a +2 and a -5. All right, subtracting polynomials can be just a tad bit sticky because I need to make sure that I take into account the subtraction for each term. Let me try to tell you what I mean. So first let's try one vertically. I'm subtracting this from that, so I need to write this one first. 8x cubed minus x squared minus 5x plus 1. And I'm subtracting 3x cubed plus 2x squared minus x plus 7. So if I'm subtracting all of those, change my pen color, that means I'm subtracting a 3x, I'm subtracting an x squared, I'm adding an x, and I'm subtracting a 7. I really just distributed that negative, that minus sign, through that parenthesis. And now I can just go for it, right? 8 minus 3 is 5. -1 minus a 2 is -3, because there's a 1 here. -5 plus 1, because there's a 1 there, is -4. And -6. And we're good to go. Next, I try the horizontal. Subtract this one from that one horizontally. Normally, you won't have to rewrite them when you are subtracting horizontally. Okay, so I need to distribute that negative sign. So that makes -5 plus z and -3. We've got squareds, squareds, but let's include the negative. Z and a z, and need one more color. A constant and a constant. So let's collect our colors, or our like terms. 4 minus 5 is -1, z squared. +9 and +1, because there's a 1 there, is 10. -12 and -3 is -15. That 1 does not need to be there. We know that, right? Cool. Guided practice. I'm going to push pause, and you guys can try these ones on your own. Come back and see if you did the answer correctly. All right, check out your answers. Make sure you got it right. All right, moving on. Multiplying. So we're going to practice a few different ways to multiply. In fact, I'm going to show you a way that's not even on here. So we're going to try things vertically, we're going to try things horizontally, and then we're going to try the box method, which is my personal favorite. So let's go ahead and try vertically. So I'll line these things up. You actually don't have to line them up in any specific order. And just like when we multiplied, I don't know, many digit numbers by, let's say, 24. Remember, we would multiply, okay, 8, 12, carry it, and then put a placeholder, and then 4, 6, 2, and then add everything together. Right? Well, you do the same thing with these, which is probably why it's not really my favorite, but that's okay. So I'm going to multiply, okay, up over and over. -2 times -6 is +12. -2 times 3y is -6y. And then we have +4y squared. Placeholder, -6y, 3y squared, and -2y cubed. Now we're lined up to collect like terms. And we have the right answer. So there is the vertical method, which is probably my second favorite. Horizontal method is probably my least favorite. When you don't have very big polynomials, it's not a big deal. But when you have big polynomials, boy, can it get messy. So first I'm going to take this x term here and distribute it through the next polynomial. Then I'm going to take the 3 and do the same thing. So I have a binomial times a trinomial, not that big of a deal. But when you get bigger numbers together, it can get quite messy, right? So first I'll distribute that x. So that gives me 3x cubed, 2x squared, and 4x. And then I'm going to distribute the 3. So let's do this. This is all of the yellow. 9x squared, 6x, 12. Now I have to collect like terms. So I only have 1x cubed, x squared, nope, x squared gives me 987, x squared, positive 4, negative 6, negative 2x, and a 12. So I have my final answer. Okay, we're going to try this problem one more time. So now I'm going to do the box. When you multiply things, you also, in a way, are finding the area. So I'm going to draw a rectangle with lots of smaller rectangles or squares on the inside and show you how I can use this box as a representation of finding the area of something. This is when I teach multiplication of polynomials in Algebra 1, because we do it in Algebra 1 also, I teach it this way because it just seems like a much easier way to keep things organized. So I'm going to multiply my row and column, and then my row and column. So I've got, x times 3x squared gives me 3x cubed. X times negative 2x is negative 2x squared. And x times 4 is 4x. Next row and column, I have 9x squared minus 6x plus 12. Now I can collect like terms. I'm adding things together, and in this case, my diagonals actually match up, so I know exactly what to add. I've got that 3x cubed. A positive 9 and a negative 2 is 7x squared. A negative 6 and a positive 4 is negative 2. And 12. So I got it all. Cool. So I call this the box method. It's really the area representation, or yeah, that's it. Okay, 3 binomials, not a big deal. Horizontal format. I have binomials, so I'm going to FOIL any combination of them. I'm just going to grab these first 2 and FOIL them. Okay, first, outer, inner, and last. Collect like terms. A positive 1 and a negative 5 is a negative 4 and minus 5. So I still need to multiply this by x plus 3, which I'm going to use the box method. You guys may make fun of it. I think it's pretty awesome. X squared minus 4x minus 5x and 3. So rows and columns. Okay, then collect like terms. X cubed And then here, positive 3, negative 4 is negative 1 x squared. Negative 12, negative 5 is negative 17x minus 15. There you go. All right, here's where we're learning special patterns. And what I can tell you about special patterns is if you can memorize them, it's worth it because it's going to make your life easier, especially this first one right here. Okay, it's the sum and difference of binomials. So when you have a plus b and a minus b, you FOIL that, and your answer is going to be a perfect square minus a perfect square. My example would be x plus 4 times x minus 4. If you FOIL this, your answer is x squared minus 16. Now, again, we teach this in Algebra 1, so we're just glossing over it pretty quickly in Algebra 2. But if I show you my work, I get x squared first, outer, inner, and last. If we see we have a negative 4x and a positive 4x, which cancel out, and I'm left with x squared minus 16, which I call the difference, which is subtraction, of perfect squares. Cool? The square of a binomial, if you've got a squared plus b squared, please note down here, common mistake that I could jump out of my skin because I try to tell my students every year, all the time, please, when you see any binomial raised to a power, do not just distribute the power because it doesn't work, okay? It's not a true thing. But I can square the first term, 2 times the first times the last term, and square the last term. Or square the first term minus 2 times the first times the last plus square the last. An example would be like y plus 3 quantity squared is y squared, 9 squared, and in the middle is 2 times y times 3, or 6y. Same here. Square the first term, square the last term, and then 2 times the first term times the last term. 2 times 3 times negative 5. Which is negative 30. Yep. Cube of a binomial, not one that I've even have memorized all that well, but a plus b cubed is a cubed, b cubed, and in the middle I have 3a squared b and 3ab squared. And if you have the difference of a perfect cube, cube the beginning minus cube the end, and then minus 3a squared b plus 3a squared b. Okay, when it's plus in the middle, all of them are plus. When it's minus in the middle, I actually alternate, minus, plus, minus. I left these on here to show you. For a, I've got 3t plus 4, 3t minus 4. So I've squared the beginning and I've squared the end with a minus in between, and that's my answer. So this right here is we call it the difference of perfect squares. Square of a binomial, square the beginning, square the end, and 2 times the beginning times the end is the middle. The cube one, a little bit harder. Cube the beginning, cube the end, and then the middle is 3 times the beginning squared times the end plus 3 times the beginning end squared. Let's try it. So this is just a bunch of examples. So I do anything bigger than binomial times binomial, I draw the box. 3x squared minus x minus 5. I have 3x cubed minus x squared minus 5x, and then 6x squared minus 2x minus 10. collect like terms, 3x cubed, and then I have a positive 6 and a negative 1. And then my x terms, I have a negative 2 and a negative 5, minus 10. Here I've got 3 binomials, so if I do the first 2, first, outer, inner, last. Collect like terms. A squared minus 3a minus 10. And then I'm going to set up the box. On the top, I'll do the trinomial. And along the side, the binomial I haven't done yet. Ooh, typo. So a cubed minus 3a squared minus 10a. Then I have 6a squared minus 18a minus 60. That gives me a cubed plus 3a squared minus 28a minus 16. Ten times 6 is 60, though. Cool. Almost made a mistake. And then we have a special product one. So I'm going to cube the beginning, x cubed, y cubed. And I'm going to cube the end, which is, and in the middle I have 3 times the beginning squared times the end. So that's negative 12x squared y squared. And then I get 3 times the end squared times the beginning. So that's 4 times 4 is 16 times 3 is 48. There we go. All right, let's try our wordy example. Since 1980, the number W in thousands of United States wells producing crude oil and the average daily oil output per well, O, in barrels can be modeled by W equals that, O equals that. T is the number of years since 1980. Write a model for the average total amount T of crude oil produced per day. So if W is number of wells in the United States and O is the output barrels per well, then I think for the total amount we would multiply this stuff, right? Cool. So I'm doing a box. You guys can use whatever method you want. I really like this one. So I'm going to have 3 by 2, negative 0.57, 10.9, awesome, negative 0.249, 15.4. So let's do some multiplication. Let's get my calculator out. So it's 575. Negative 0.575 t squared times 0.249. Negative times negative is positive, so this is 0.143 t cubed. The next will be negative 2.71. Goodness, we're not going to talk how to do significant figures. That's really a science thing. So round You can round to whatever you'd like to, as long as you leave some digits there and you do it correctly. If you start rounding incorrectly, then you can lose some points. But if you round to something that I didn't tell you to, well, I didn't tell you what to round to, so I'm just going to go 2 after the decimal place. Cool. 0.575 times 15.4. And that's a negative. I didn't get my variables. I didn't get them here either. Sorry, I'm going willy-nilly, aren't I? This would be t. Cool, now I can collect like terms. I have, did I do all my negatives right? Yes. Okay, so I have 0.143 t cubed. These are like, so negative 2, 2.71, plus a negative 8.8. This should be a t. These are both t's, so collect those like terms. Negative 136.45 plus 167.86, 31.32 t, and then 8,439.2. That right there represents the total amount of crude oil produced per day. Yep, pretty close to the answer. We have some rounding differences, but that's all right. So the total daily output for oil is modeled. T is measured in thousands. But if I look at the problem again, it wants average total amount produced per day in year 2000. So the problem said since 1980. So we need to actually substitute 20 in for our model. So 1980 to 2000 is 20 years. So I'm going to substitute t equals 20. Do some math. I'll be right back. I get the total production as 5,605 barrels. I have to be off by a factor, though. Nope, that's right. Go back and look at the problem. It's in thousands. So, in essence, that moves our decimal point to about 5,600,000 barrels. So the model below gives the average depth D in feet of new wells drilled and the average cost per foot C in dollars of drilling a new well. In both models, T represents the number of years since 1980. Write a model for the average total cost of drilling a new well. So I'm going to multiply these, and you can try to multiply them too, and I actually get T equals 59.1 T cubed, 1,393, rounding, T squared, 20,057 T plus, ran out of room, 318,394. Cool. All right, daily homework quiz. I'm going to write answers down for these, but I'm not going to show my work. If you want a little bit more practice, make sure you're doing it right. I could use these on a quiz or a test too, which is sort of cool. Go ahead and try them, okay? Okay, there are the first two. Next ones, we're multiplying these. Answers. And the last word problem, floor space. area, okay, for all three stores. So I've got floor space of retail stores. A, B, and C can be modeled by A, B, and C. Write a model for the total amount of floor space for all three stores. What's the total floor space if this X equals 50? So I'm actually adding these together. Oops. Okay, total area, adding them together. Negative x squared plus 247x minus 7. And if I plug x equals 50, my answer is 9,843 feet. Oof, sorry. Feet squared, its area. That's it.